Good morning, good afternoon, and good evening. My name is Rob Bunger from Schneider Electric, and I am very excited to host a webinar where we have some experts that, I'd like to say have been there and done that with regards to liquid cooling, right? A lot of people are deploying liquid cooling right now, but the number of people that have gotten their hands dirty and understand all the intricacies from designing and deploying and we have two of those experts right here. So first, I'd like to introduce Greg from Motivair, and we also have Vinod from Lenovo. So Greg, why don't you introduce yourself?
Sure, happy to be here. So brief introduction, Greg Alexander here, a senior thermal engineer with Motivair by Schneider Electric. So I come by history of a lot of experience in the high performance computing market. Started my career with Cray and then onto HPE, mainly focusing on, 1U very dense, 100% liquid cooled servers with cold plate design, conduction plate design, and full thermal systems to figure out, what the pipe flow and the layouts might be. But now that I'm at Motivair, but, focusing, taking another step up the thermal chain, that is, rather than focusing directly at the GPU, looking more at the CDUs, the coolant distribution units, and how we're actually deploying fluid to these ITE racks.
Great, thanks, Greg. Thanks for joining us. And Vinod, please tell us about yourself.
Yes. My name is Vinod Kamath. I work at Lenovo in North Carolina. Before joining Lenovo, my team was part of IBM, and we did dense, high performance liquid and air cooled solutions with x86 silicon. And I was the architect in that space for that products. And as we transitioned to Lenovo, we brought with us technologies that we had developed for high dense warm water liquid cooling solutions that delivered energy efficient computing in the high performance computing space. And now I lead the architecture for both high performance and AI system designs here at Lenovo that we deploy with essentially 100% heat capture liquid cooled solutions.
All right, fantastic. So we are going to get a little bit technical in this discussion, but not crazy. But I want to start off pretty easy. And so, Greg, I want to start with you. And
Sure.
why is water better than air fundamentally?
We get down to the physics, and when we're looking at your properties of fluids between your air and your liquid, if we have our mass flow rate equation, that is the Q dot equals M dot times Cp times delta T. Q dot there is your power, M dot is your mass flow rate, Cp being your coefficient of thermal capacity or specific heat capacity, sorry, and delta T obviously being your temperature difference between the start and the beginning of the fluid. So when we look at, air versus fluid being, liquid, either DI water or PG25 are typical in the industry. You have a much denser fluid, so your mass flow rate could be a lot higher for liquid cooling versus air cooling, and your specific heat is much better with water. So I kind of like to think of specific heat as kind of like the bucket of how many joules you can carry, right? If you have a larger bucket, you can carry more heat away from the system. So generally, if let's call a 500-watt GPU, right? That's your Q, and that's going to be fixed. So if you have to cool that via liquid or via air, your air cooling will have, lower mass flow, lower CP, so that delta T is going to be a lot larger. Whereas once you have fluid in this mix, you have much higher mass flow rate, much higher specific heat capacity, you can have a lower delta T. And so it just makes the whole system more efficient.
Yeah, fantastic. And yeah, and Vinod, as you guys were probably making decisions many, many years ago on when you want to switch an air-cooled server to liquid, what was the process that you went through on that?
Good question, Rob. Uh, Back in the day, we didn't have to deal with 500-watt GPUs that Greg just spoke about, right, some years ago, about a decade ago. But what we were beginning to see in the marketplace, especially in Europe, is high energy prices. The cost of energy in Germany was 20 euro cents a kilowatt hour. This was in 2010. So if you looked at the total cost of deploying and operating a dense high performance computing cluster, if energy pricing was important, and then secondarily, if there were some local rules to manage energy more efficiently, reduce water consumption, etc., what we began to see is, to Greg's point, the efficiency of liquid drove the ability to consume minimal amounts of energy to cool and maximizing that to compute important and deliver. So we first delivered back in the day a 10,000 node cluster, x86. It was a benign TDP on the CPU, but over the operational life, the customers saved a lot of money. And that then began the journey at initially at IBM on x86. And then, over time, as we have seen in the dense x86 and now GPU space, delivering extreme efficiency and now performance, to Greg's point, on the ability to capture more heat with smaller volumetric amounts of fluid than air.
Yeah, I find it interesting that some of the early customers you had were really focused on efficiency, which has been known about liquid cooling, but now we have the dual benefit of course, cooling the hottest chips that are coming out of the market, and, the efficiency is almost the side benefit, or you can deploy more compute in the same power envelope now because of the efficiency gains that you have, right? Um, so one of the things I'd like to dig into is really what's happening at that cold plate, right? I've heard terms, there's T case, there's thermal resistance and things like that. How does that all stack up in when you're thinking about the performance of liquid cooling? Greg, we'll
So, want me to start?
Yeah.
Sure, yeah. So, we can go into the absolute nitty-gritty of it, but I think we wanna keep it a little bit more simple, right? Like, from the, laws of thermodynamics, that kind of is what derives that original equation I mentioned. But even that can have some intricacies and a lot going on as far as, defining all your different terms. And so what you mentioned thermal resistance. It's kind of a catch-all to, I don't wanna say dumb the system down, but make it more palatable. Because actually, if you take the typical equation for electric resistance, V equals IR, there's a complete analogy between the two, right? So if you have thermal resistance, that'll be equal to your resistance in ohms, right? In the electrical analogy. Your current is going to be more your delta T. No, I is going to be your Q. It's your, yeah, sorry, your power flow through the answer. And your delta T is then going to be your voltage, kind of like your differential between the two points that you're delivering your power, right? So by making this, you kind of massage the equation to have a thermal resistance, typically in degrees C per watt is the units that you use there. That gets it down to there's kind of one number that kind of gives you a better idea of how your efficiencies are, right? So for a quick example to kind of again compare air to water, typical, the highest end air cooled heat sinks that are going to be on these GPUs are anywhere from like zero point 0.1 to zero point 0.3 degrees C per watt. And your typical high performing liquid cooled cold plate is an order of magnitude better at 0.02. And that's typical, right? There's some that are not as efficient. There's some that get down to 0.01 or even below 0.01, depending on some real like intricate geometries that go in there. Um, but that's just kind of highlighting that, liquid is really an order of magnitude better than air from a fundamental physics perspective. Um, if we wanted to dive a little bit deeper in some of that, there's some other, analogies. There's capacitors, right? All those different things you might have in that V equals IR analogy. There's similar thermal equivalents. But
Yeah. Great. I appreciate the electrical analogy. It kind of helps me out.
exactly, yeah.
um, and something that has been discussed a lot, and Vinod, I want to direct this to you, is there's a bit of a there's PG-25, which I think the industry is really I don't say settling on, but you hear a lot about that right now as the large scale liquid cooling is getting deployed. And then there's also DI water, which if I believe that Lenovo has quite a bit of experience with DI water. And if you could kind of talk about
Yeah.
the differences and choices.
Yeah. So clearly, as you state, at least for single phase liquid cooling, there are two fluids. Uh, DI water, which is what Lenovo has been using since 2010, has performed reasonably well, reliably, and it does have the promise of a bit more efficient heat extraction. And also in some geographies, and this is a geography specific statement, some countries, they prefer somewhat fluids that are more easily environmentally regulated, right? So that does, though, require the customer, the solution provider, to maintain the fluid chemistry very well and carefully. We know that DI water is biologically sensitive. It can go bacteria because it's water, right? So you need to maintain the fluid chemistry quarterly. And so long as you are able to manage that fluid chemistry management, our history is that it has worked. I'll speak to PG25 next. What we are beginning to see in the industry is a proliferation of liquid cooling solutions. It's no longer the research labs or scientists who are using this for computing, right? We are using it in enterprise environments, in environments where the customers do not have domain expertise, or maybe the suppliers that are part of the ecosystem are so varied now that for them to independently manage fluid chemistry is non-trivial. So PG25 helps in that effort in the sense that at 25% glycol, it is biologically inert to first order. You still need to be careful, but it is biologically inert. Once that's done, then it's the chemistry that has to be maintained. Though the chemistry has to be maintained, it is important that even when you do PG25, that you have a maintenance cycle that manages it. Because when that's done right, you get a reliability that is significantly better than any air-cooled system. So well-managed water or reasonably managed PG25 will deliver the efficiency at any scale in any environment that the customer wants.
Eh, Okay, that's interesting. So when you just to make sure I understand something that you said, I guess when you look at an air-cooled environment, and I know there's kind of be dust and everything else. So even when you get to water, you have found historically that you'll have better reliability and performance with a liquid cooled system over the air.
Yes, yes. I mean, so there is evidence of behavior that we have. Unfortunately, we don't have a white paper that we have released internally at Lenovo, but
Yeah.
the evidence that we have suggests the following. And this is true from the thermal resistance that we had talked about, and then the essential, advantages of liquid, right? Temperature differential that the liquid enables for silicon is in a very narrow, small range. You are then, in addition, able to maintain the fluid flow rates and temperatures almost to within a few percentage variance in its mean value,
Mm.
right? Your flow rates are, plus minus 2% on the rack. The temperatures are bounded by a degree with some PID tolerance, maybe. That is not true in air-cooled systems. Air-cooled systems, the fans will dynamically dance with the device temperatures, changing flow rates and changing silicon temperature. So what we have seen is the fact that the silicon operates in a narrow range allows the ability of the silicon to perform more reliably. There may be failures, but the failures are not temperature driven. They may be driven by some firmware issues or some updates that didn't perform well due to some, silicon coding challenges that we see.
Ah, that's interesting. Um, Going back to uh, water chemistry, since we talked about that a bit, and this is both for Greg and you, so you mentioned that for DI water that at least your practice was typically every quarter.
Yeah.
To test and all that. Is it the same for PG25, or what have you seen typical for PG25 maintenance?
Right. So I can speak to, what we have done. So our expectation is that with water, clearly there's an expectation of a quarterly maintenance. It's easily done, but needs to be done. On PG25, there's an expectation that after maybe some early chemistry maintenance certification, right? You can maybe, it does depend on the end customer. Okay, you might be able to then relax that sort of quarterly expectation to maybe twice a year, and maybe keep it at that. But my personal perspective is that at the scale and the expense that these servers cost, right? You want to maybe manage that fluid chemistry carefully and spend
Sure.
a little bit of money, right, in validating it twice a year. It's not a big deal. Easily done. I mean, it's trivial, I think, once you establish a practice.
Yeah, it's nice that you bring up cost, because it's a drop in the bucket compared to the cost of the systems we're cooling here. So a similar perspective on my side. It's typically going to be more prescriptive as far as how much you need to be sampling and watching the DI water, and that's kind of why people choose, or why the industry is focused more on PG. I think there's this perception that it's this easy button. Once you do PG25, there's not going to be any biogrowth, and that's not necessarily true. Like you said, you still need to make sure you're managing, and on commissioning also make sure that that's well established. But
Yeah. Since we own, the server provider, right? We own the warranty of the server, so it becomes absolutely critical that we know what that is. And I would not second guess that expectation of managing fluid chemistry in any fluid that we choose.
Yeah, and from what I've heard that if it gets out of control, it can be a real nightmare to recover from that. Is that
Right? And while I don't want to, make it a scary thought, right? We are in these next generation of designs, right? Going to finer pitch cold plates. I mean, there's an expectation of 25 micron filters, and then the fin density sort of is not going to be a simple sky design long term, right? It's going to have some really 3D complex geometry on the inside. So then that, anything that grows is difficult to dislodge. So you want to be careful. But the point is you can, and there's evidence. We have customers that have deployed, water-based systems and operated successfully for 6 to 8 years. I mean, so there's it's not like it's new science.
That's a great
point. Engineering.
Yeah. So shifting a little bit now, we've talked about what's happening at the server level and a little quality, but how do we deliver the right water to the servers? And so that brings us to the CDU. And so Greg, purpose the CDU. What do what are the main functions? What's it there for?
Sure, yeah. So, I mean, at the end of the day, there's some major components that it makes up. It's got a heat exchanger, some level of pumps, typically filtration again to manage that fluid chemistry, control valves, pressure meters, flow meters. All these things kind of come together to be this barrier, right? So typically, there's two different loops in the ASHRAE nomenclature, and I think it's pretty well accepted now. It's TCS and FWS. TCS is technology water system, or technology water cooling system, rather. And that's the direct fluid that we've been discussing that's going right to the direct to chip cooling. And then you have FWS, which is your facility water system. The facility water system has been around for a long time, right? Because when you have these air-cooled servers, they're typically going to be spitting that hot air out into the room, and that heat has to go somewhere, law of thermodynamics, everything. So there's cracks and craws on the sides of the walls that then transfer the heat from the air into a facility water system, which then goes up to your chiller on the roof, or evaporator, water side dichotomizer, all these different other technologies at the end of it. So the CDU fits into this ecosystem as kind of that barrier between what needs to be a very clean and controlled fluid that's going to the chips, from facility water, which historically might have been around for a long time. There's wrought iron pipes. There's a lot that can go on there that we don't want to get anywhere near the IT equipment. So, yeah, at the end of the day, I think barrier is the best description of what a CDU is.
Right. Yeah, I've thought of it as to go with your electrical analogy, it's sort of like a transformer, right?
Sure.
It separates,
One curve from the other.
yeah, the quality, the temperature, the pressure, and all that can be controlled. So, okay, that's great. Now, there's a lot of different kinds. You have everything from rack CDUs, that just service the IT equipment in the rack, to very, very large CDUs and thus large TCS loops. I think if you both could kind of talk about uh, the trade-offs on deploying those different types of things. And then I'll start with you. I guess, what have you seen? And
Yeah. Prior deployments of high performance computing, right, required us to deploy high level solutions because it was a single physical location. The customers were buying, minimum 10 to 40 racks, and on the extreme end, about 100 racks. So if you do the TCO, if you recognize that customer is able to manage fluid chemistry well, you would do an eye level half a megawatt or about 1.4, 1.5 megawatt CDUs, because that's efficiently deployed. You can deploy in topologies. I'm sure Greg will get into it, n plus n, n plus one, or whatever. But what we are beginning to see is this rapid desire for quick AI consumption and enterprise consumption of these things, right? In that model, you don't know what the facility water circuit is. You don't have the time to redo it or re-engineer it, right? So you can still maybe manage an eye-level version and, sort of connect it directly to a CDU, but it is also easily consumed when a CDU is part of the rack, because then you can sort of separate the fluid chemistry at the rack level. So I think the short answer is we'll see both, though we are seeing more examples of in-rack in the small consumption model where customers are just buying a couple of racks.
Yeah, I think that the phrase I like to, I'm not going to take credit for this phrase, but rack and stack is what people like to call it, right? Where you're able to, deploy it one rack at a time. It already has all the liquid cooling integrated into it. You connect it up to your facility system and it's good to go. So they can roll it onto the floor and immediately start churning tokens. Whereas when you have to have what we would call a floor mount CDU that's servicing multiple racks, but typically much higher capacity, then you have to deploy in larger chunks.
okay, yeah, uh, yeah, I like that fast deploy. Now, from a trade-off perspective, I would expect that if you were to multiply the amount of heat transfer rack base, the cost of a CDU in every rack versus a centralized system, and the maybe chemistry testing, service that you'd want to do, that in the potentially long run, that the rack CDUs could end up being more expensive.
Yeah. Well, so I'll give my or our perspective at Lenovo, right? So it actually depends in the sense that, if you had a large N plus N location or N plus one location, right, where there is a service engineer available because of the size of the deployment, it is probably always true that the sort of the data center level CDU, right, the 1.5 megawatt kind of thing, right, is easily and more readily managed and more optimally managed for cost.
Mm.
Because somebody is there, they are managing and monitoring this thing, right, every day. They are experts. But even if you have a large deployment and you don't have the local expertise, then the question that you might want to ask is, do you have a service contract with a CDU vendor where, right, they are sort of still managing that at the node level or the rack level, right? So it's in rack CDU integrated, but managed by the provider of liquid services, and that cost may be something that Motivair can comment on. It may be higher, but it need not be higher.
Yeah, and I think total cost of ownership is a good phrase to use here because I can't get into the business of it. I'm more the the physics guy, the nerd in the back closet. But when it comes to looking at total cost of ownership, there could be some things to consider as far as service level and what's easier to deploy. I think from a fundamental physics perspective, maybe an analogy I could use is on the air cooling side. It's really just an economy of scale where you're going to get potentially more efficient gains from a 1.5 megawatt studio as we've been using. If you compare that to like an air cooled system, imagine like 140 millimeter fans running on all those servers versus 2 or 3 large blowers on a fan wall. It's pretty clear, obviously, which one's going to be more efficient at moving, in bulk, a large amount of air. So it's not a direct comparison, but it's in an economies of scale.
Yeah.
fashion.
Fantastic. When we talk about heat transfer, getting back to the physics, there's still a lot of different liquid cooling technologies out there, and two-phase direct to chip is something that you hear talked about a lot in the market, and I'd like to see if you can address what that is and why it's good and uh any challenges to deploying it. And Greg, I'll start with you on that.
Sure. Yeah. Yeah. It's certainly an exciting field. I mean, obviously, refrigeration has been used in the air conditioning cycles for what 100 years now. Maybe not that long, but we've been aware of the Carnot cycle and all these different technologies that use ways to vapor compression allow for refrigerant to cool things at higher temperatures than what they're trying to cool to, right? And so if we get back to the physics part of it, what you're doing is you're boiling a fluid, right? And so what you take advantage of there is the latent heat of vaporization. So essentially you're going to be providing liquid refrigerant to the cold plate, and then it boils directly on the heat source of the cold plate, and then leaves as typically a vapor mixture. It's not going to be leaving as 100% vapor. For some safety reasons, maybe we can get into, but the idea is it's a lot more localized heat flux that you can get out of a very small package. Whereas, so if you compare that to like a single phase system, you're kind of in a linear path, right? Where if you need more cooling, typically you're going to need more flow because that's your knob that you can turn. Um, so you typically will need a lot less mass flow because a lot of that heat is not necessarily just going into heating up the fluid; it's going into boiling the fluid. So obviously your velocities might be a little bit higher on the vapor side, right? So there's going to be some pressure drop considerations there. But the idea behind two phase, being superior or not superior, that's up for debate, right? But the idea is that at the local GPU, you're able to get a much higher heat flux, and that's why you would end up using that.
Okay.
Another advantage to that right is you have a single boiling temperature. So a lot of GPUs are getting some really weird mixed topologies these days, where you might have hot spots in spots that aren't typical to CPUs from 10, 20 years ago. And so those hotspots then are managed because the entire surface is just at the boiling temperature. You don't have to worry about, heat being in different spots within the package.
Interesting. Yeah, Vinod, is this something that whatever you can share, if you guys researched or your thoughts on that?
Yeah, so the way I'd like to answer this question is the following, right? So at the end of the day, as a server solution provider, what we bring to the sort of end customers is technologies that are necessary to keep the silicon working reliably and efficiently, right? And have sort of an expectation that the invested technology has some life, right? It's available and then it's managed to the customer expectations. Today, what we are seeing is from the data available to us that over the next few years, right, we can still keep using single phase liquid cooling and deliver the cooling expectations of accelerators that are pushing, more than kilowatt and a half, right? I mean, there's data available in our labs that document that behavior. So for us, the perspective that we have in this space is use the technology that works and research the technology for the future, right? Because it is to the point that Greg meant. I mean, you may run into a scenario where there are some local temperature gradients that need some, fairly aggressive heat transfer because the power densities are high, maybe not the power is high, or maybe the rate at which the power is increasing is not natively aligned to the most efficient heat transfer, right? So we are researching these technologies. We are planning for the future, but it's not something that we absolutely need to deliver the silicon performance in 2026 and 2027. But to the point that has been made, these technologies exist today. I mean, you will see solution providers delivering two-phase cooling, and there's a place for that based on their end customer expectations of efficiency or reliability that they want. But it is not necessary for 26 products or probably even 27 products, as best I can tell you.
Perfect.
Yeah. And I think an important point to bring up too is the, deployment needs and there is really no free lunch here, right? Like it's all well and good to look at, just at the cold plate and say, wow, this is so much more efficient here. But then what are you going to do with that vapor? In a typical, single phase liquid cooled system, you have some simple hoses, maybe even just some quick disconnects, that can, be able to swap out servers. But once you put high pressure vapor into the mix, hoses are less reliable. You need to have a lot more pressure containment. There's safety concerns for, let's say you overboil, and I mentioned 70% of a vapor air or vapor liquid mixture, right? If you get into superheated vapor, then your pressure is really going to start building up because there's nowhere for that heat to go other than just higher temperature vapor. Higher temperature vapor gets very high pressure. So there are things that come with a two-phase system that are not inherently better than single phase. I think single phase, like you said, for today is perfectly reasonable. And knowing when that switchover point is, I'd like to go get a lottery ticket if I knew.
Fantastic. That's great. Thank you. There's been let's see if we're going to talk like, so let's talk supply water temperature to the rack to the chip.
Yeah.
I think it was interesting, and I think at CES at the beginning of this year, kind of in a public forum, Jensen from NVIDIA had said, "Hey, 45C water, and what's that mean for the facility?" And let's talk about what do you guys recommend, or what do you see, and the supply water temperature world. And Vinod, I'll start with you.
Yeah, so you bring up a good point, right? So in January, there was a discussion of warm water. Maybe it was the weather that made that happen, right? So it's freezing out here in North Carolina and the Northeast, right? So, I mean, jokes aside, though, when we started liquid cooling, it, like I mentioned earlier, right, it was an energy efficiency story. And in Munich, the customer also had an expectation of minimizing water consumption. So they had a dry cooler on the roof. The dry cooler has an expectation of operation temperature. I mean, even though it's Munich, in August it does get warm, right? So we designed our platforms for W45 back in the day, and now we have a TCS at 45. I mean, that W45 is difficult to maintain. So we have a W40 based cooling solution, and we have deployed it essentially in a whole bunch of our customer environments around the planet. Though what we are also seeing is customers who are retrofitting their air-cooled data centers that have chilled water to liquid. Well, they're not deploying a dry cooler. They are using their existing data center facility infrastructure. And in that environment, it's W18 or 17, right? So that's the water temperature coming into the racks or the CDUs. So we see a range, though with clarity, the expectation of the higher water temperature stems from an expectation of optimizing for energy resources, which includes water, right? I mean, water is a scarce commodity. So the more you can use free cooling or a dry cooler, right, you can maybe get better energy for compute or token creation, which is the metric today.
Yeah.
Right.
So it's interesting to know that you guys have been doing 45 seawater and 40 for a while. So that's fantastic. And in a term, and this is in my learning, I'm going to ask you a question, Greg. I hear
Yeah.
about a CDU, and especially when you're trying to get as much free cooling as you can, there's a talk about, the approach temperature across the heat exchanger. What's that mean in the system design?
Yeah, so approach temperature delta, ATD is what it's typically referred to, is kind of it's a temperature difference. So it's one temperature minus another to give you some number, right? And that's going to be your water, or I guess in some systems, obviously, if it's air cooled, to your fluid, for instance, your fluid going to the IT equipment, uh, minus the incoming facility water temperature, right? So if you have a cold water temperature coming in here and a slightly warmer temperature going to the equipment, that difference between those temperatures is your approach temperature delta, ATD. And so kind of getting into the whole ecosystem, right? The chip to chiller story is we have heat at the chip and it has to go through all these different stage gates to get out to the air and go off into the atmosphere, right? And the chiller discussion and dry cooler between those two, right? So each step you're going to have another ATD, right? So between chip from that fluid in the CDU going to the facility water, there's going to be a bump in temperature. From the facility water to the refrigerant loop, in if it was a cooler, there's going to be another jump in temperature. And so as you in typical trends, right? I don't want to name specific numbers, but if you can decrease that ATD, you're going to increase your efficiency of your system because you have less of a bridge of a temperature gap to go to, right? And so the 45 degree discussion is great because then you can run your system at hotter temperature, and then as you step up to hotter and hotter temperatures, then your final kind of I don't know necessarily ATD, but your difference between your ambient temperature outside and your heat dissipation is going to be greater and greater. So you have more capability to dissipate that heat in the environment, right? And that's the whole goal of trying to go to dry coolers, right? You don't need a refrigeration cycle. You could just dump the heat out for free.
Right.
So I guess does that answer the question, or do we want to go?
Yeah.
Bill, I kind of ramble a little bit, but
Yeah, let's for a CDU very quickly. Like, what's a typical the temperature difference or that approach temperature built
Sure.
within a CDU between the facility water and the TCS? What are those? What's that number typically?
yeah. So a good metric to go by. So ASHRAE very recently, so SSPC 127 is a special group devising the method of test for CDUs and other components within the data center. So they've recently put out an addendum that qualifies that method of test to be set at 4 degrees ATD. So that's going to be 4 degrees between your incoming water to your ITE versus your cold water on the facility side. That's not to say that all CDs have to operate at 4, and they don't, right? So there can be trade-offs either way, which direction you want to go. There's this, but in general, as you want to shrink your ATD, yeah, that's going to affect your CDU designs for sure.
Yeah.
But 4 would be typical, based on ASHRAE's point of view.
Okay. All right. So we're getting towards the end, and I'm going to do some quick wrap up questions for you. So if I'm going to have two separate questions, and if you were talking to a designer that might be designing their first liquid cooling system, what advice would you give them? And Vinod, I'll start with you.
Yeah, so what I would say is if the person has never deployed these kind of solutions before, I would say start off by reading the ASHRAE and OCP guidelines. Start there. I mean, because that's sort of vendor agnostic, and I'm all for that, right? So once you understand what the data certainty and the knowledge is in the industry, right? The terms, the expectations, the way to manage it. Once you do that, understand what the lifetime of your installation wants to be. Are you planning this for 1 generation, 3 generations of products? And sort of what is the level of engagement that you want from the server vendor next to help engage with you to understand what that solution path might be based on their technologies in your data center environment, right? At the moment, I think all the tier 1 server vendors are aligned to deliver essentially reliable high performance computing solutions. I believe that at Lenovo, we started that journey. So in that model where you are following industry standards and then engaging with the server vendor. Together, you will basically find the right solution path identified for your data center environment, whether it's a new one or an existing one, because we have seen examples where at Lenovo, we have engaged with a lot of enterprise customers that they have redone their air-cooled environments with liquid cooling, and that transition has gone smoothly. It has to be done right and with good conversations, but it works.
Yeah, that's great to hear.
Yeah.
Okay, great.
Yeah. So I would say first off, congrats on making the right steps towards improving your data center efficiency. Right. But I think all jokes aside, I think the best thing I can, there's two things, right? Is one, just communication, right? As Vinod mentioned, this is a wide system and there's a lot of different moving parts. And so first of all, reading up on your ASHRAE and your OCP guidelines is a great start to kind of get an understanding of what a liquid cooling system is. But then when you go to deploying, there's the server manufacturer, there's the CD manufacturer, there is the facility that's managing the data center. There's going to be your chiller maintenance, all these different aspects that might be in different groups and might get siloed as far as who's talking to who. And so kind of encompassing the entire system and thinking about all the different levels of that and making sure that you're getting all of those parties talking together. It is the best way to deploy, and make the right solution. I did mention two things. Yeah. So then I think the second thing, just kind of a general term, just to kind of throw this out there. So LPM per kilowatt, that's kind of an industry standard way to talk about if you're going to deploy a, say, 500 kilowatt system, that's relatively small these days, but let's say that's, a couple racks, something like that, right? You can generally assume that 1.5 LPM per kilowatt gives you the total flow rate that you might need, right? And so that's kind of a general guideline for sizing your total CDU system, that kind of for your power. That's not to say that your power might be constant, right? You might be upgrading servers over time. So maybe you want to consider what, again, as Vinod said, the total life cycle and how much power you might be, consuming in 5 years, 10 years on the same system.
Yeah. That's great. I love thumb rules 1.5 and I'll specify liters per minute per kW LPM.
Yes.
Yeah.
Thank you.
And it's okay. All right. The last question I have. All right. So we've gone through design. Now you're talking to a data center operator who's installing and operating their first liquid cooled system. What advice would you have for them? So again, I'll start with Anand.
So assuming that the gear is on site, right? The first thing that you want to do is establish the cleanliness of your TCS loop, assuming you have it, right? So this is absolutely critical, because if that's not done right, the first step is not done right, you will then cascade and create a whole set of problems that you may not know at time T0 that will show up over time, right? So typically what that means is making sure either the solution provider, may not be the server vendor, right? Sometimes they are secondary providers, right? Responsible for the maintenance, have documented to you that the servers and the CDUs will be connected to a loop that are going to be of perfect chemistry, right? Once you establish that and you have the servers that have been sort of well vetted or calibrated, from the supplier connected, you want to be sure that you have the right fill and drain process, because in some cases, these servers will not come pre-filled with EMPG25. They may be deployed on site. In water, clearly it's deployed on site, right? So you want to make sure you're doing the right fill and drain process. And then when you power the servers on, once you establish the fluid flow rates and temperatures are set right, you want to then establish, using your baseline tests, things like heat capture. Do you know the amount of heat the servers or racks are dissipating from your CDU and the m dot Cp delta E that Greg led with? Do you have certainty that the amount of heat that you knew that the liquid is going to be captured is actually being seen running workloads, right, at time T0? Because once you establish that, the flow rates are right, that the DPs are right, and as we talked about, the fluid chemistry is right. And once that's done, right, then it's a simple fluid maintenance, cycle that you follow, and you have a clean, reliable, high-performance computing environment.
Fantastic. Great. and gray.
Yeah. So I guess my response to the previous question is probably, analogous here too, about communication, right? So to the Nod's point about, making sure we have a very clean fluid, I'll use an anecdote horror story that I've heard of where there wasn't communication and there was TCS loops that were installed, right? That might have been open to the air, and then there was maybe a facility contractor that was doing some drywall work in the same room, right? Obviously not a very clean environment. But that could have been avoided by, again, communication between all parties in the data center design. So just making sure that we're keeping that communication line open so that all facilities know when stuff is being done to keep that fluid clean. As far as the second point, kind of getting back to the circuit analogy, the V equals IR. If you look at that analogy, that can be used for, parallel and series resistances. And if you consider the flow resistance of the network as well, that's actually a third analogy that fits the same V equals IR. There's thermal, there's current, and then there's, flow network modeling, which would be your pressure drop in designing how much flow goes to different servers, right? And so if you have a row-based CDU that's providing fluid, then you have two different servers of two different flow resistances. They're going to get two different amounts of flow, right? Because the flow is going to take the path of least resistance, right? So just a key point of advice is to consider that when you're designing your system. And typically you're wanting to use equal servers of equal pressure drop so that they all get equal flow.
Right.
As a tip.
Yeah. Fantastic. Should anybody be afraid of deploying liquid cooling?
No. Heard, but I think we're well past that.
Yeah, that's great. So I want to thank you very, very much for your time. I know you're both very busy, and again, you having people that have been there and done that for quite a number of years is super valuable to the to the industry. So again, thank you for your time today.
Of course, you're welcome. Happy to help educate and keep things simple.
Great. All right. Thank you.